Welcome to this lecture on process control, chapter 3, first order systems. In the previous few classes, we have been discussing the dynamics of first order systems. So in this class, that is, we have been seeing the response of first order systems for different types of inputs. So in this class also, we will see the response of a same first order system and study its dynamics for a particular type, for another type of input forcing function. We'll do this by means of solving an exercise problem. The problem is this: a thermometer having a time constant of 0.2 minute is placed in a temperature bath, and after it comes to equilibrium with the bath, the temperature of the bath is increased linearly at a rate of 1 degree per minute. So what is the difference between the indicated temperature and the bath temperature at 0.1 minute and 1 minute after the change in temperature begins? So these are two questions, A and B. There are two more questions, part C and part D. So we will solve these questions, and this exercise problem is taken from the textbook Process Systems Analysis and Control by D.R. Kaufner. Now, after the thermometer comes to equilibrium with the bath, the temperature of the bath is increased linearly at a rate of 1 degree per minute. So what type of input is this? How is the temperature of the bath is going to change? It is increasing linearly at a rate of 1 degree per minute, at a constant rate of 1 degree per minute. So this is a linear input or ramp input. This is a linear input. If this is the x, is the small x is the surrounding temperature, and small y is the indicated temperature of the thermometer as per usual notation. Now if you plot in terms of the deviation variables, capital X, and if you plot this input which is varying linearly at a rate of 1 degree per minute, so it is going to be a linear input, straight line. We plot in terms of capital X, we plot in terms of capital X or small x, it is going to be a linear input. But if we plot in terms of small x, the actual variable, it will start from xs. We don't know what is the value of xs. It will start from xs. If you plot in terms of deviation variable capital X, which is x minus xs, it will start from 0. It will start from 0. And this is the rate of change. This rate of change is how much? The slope. This is m. We call it as 1 degree per minute. So it is changing at a rate of 1 degree per minute. So how do you write the input equation? Input is linear input. How do you write? X of t equal to m into t. That's the input equation, which is the equation of a linear input or ramp input. Linear or ramp input. We have discussed this earlier. Now how do you find the response? Why? By the usual method, by taking Laplace transform. So take Laplace transform of this. X of s equal to, what is the Laplace transform of t? T is 1 by s square. 1 by s square. And if you substitute in the transfer function, y of s equal to xs into gs, that is equal to m by s square into, what is the transfer function? First order transfer function of thermometer, k by tau s plus 1. Now if you take inverse Laplace, you're going to get y of t. So what is the Laplace inverse of this function? What is the Laplace transform of, sorry, what is the L inverse of this? Inverse Laplace of 1 by s square into tau s plus 1. So this has been discussed in detail in the derivation has been done earlier in one of my earlier lectures, which I think is PC16. So refer to my lecture titled PC16. The link for this is given above and below in the description. So if you have seen those, if you've seen this lecture where this inverse has been found out, what is that inverse? What is the inverse of this function? So the inverse Laplace of this function, as we discussed earlier in this PC16, is this. The inverse is mk into t minus tau into 1 minus e power minus t by tau. In this, when you derived this inverse, these constants were not there, m and k. Now these constants are there. That is the only difference. I had derived without any constants, simply for 1 by s square into tau s plus 1. Now these two constants, m and k, are there in the numerator. So this is the inverse, y of t equal to this. Now, what is the question? Question is, what is the difference between the indicated temperature and the bath temperature? Indicated temperature is y, bath temperature is x. So what is the difference between these two at 0.1 minute as well as 1 minute? So that is a question. The difference between the indicated temperature and bath temperature. The bath temperature is x, the indicated temperature is y. What is x minus y? That's all. Now small x minus small y is the same as capital X minus capital Y. You will agree with me because capital X is x minus x's and capital Y is y minus ys, and x's and y's are equal. X's and y's are equal, so small x minus small y is the same as capital X minus capital Y. By the way, this is also known as, even though it is not mentioned here, this is a error. This is the error at that particular time. That is the difference between the indicated temperature and bath temperature. So x minus y, you have the equation for x, m into t, and you have the equation for y. The equation for y and equation for y, x. So let me substitute here. So x minus y equal to, x is simply m into t, and y is this equation. Y is this equation. Y is this equation. Only thing, when I write this, I'll simply write k as 1, because k is 1 here. So this is, this k is 1, right? K is 1. So I taken k is 1, because not taken thermometer, k is 1, the gain. So m into t minus tau into 1 minus e power minus t by tau. Now if you simplify this, what will you get? If you simplify this, you find this t and t cancels, so you're left with only this term into m tau into 1 minus e power minus t by tau. So this is the difference between indicated temperature and bath temperature. Also, you can call it as an error. You can call it as error. So what is this value at 0.1 minute and also at 1 minute after the change in temperature begins? So all you have to do is substitute t equal to 0.1 minute. So a part is t equal to 0.1 minute. So how much will be x minus y? Substitute in this equation. Substitute. So substitute in this equation for t equal to zero point 0.1 minute. If we substitute here for t, if we substitute 0 0.1 minute for t, you substitute 0 0.1, substitute 0 0.1 there, and the answer you will get is 0.0786 degree. What is this, Celsius or Fahrenheit? What is given? Not mentioned. What is the unit of temperature is not mentioned. So okay, leave it. So it is, the difference is 0.0786 degree. So at 0.1 minute, the difference between indicated temperature and bath temperature is 0.0786. Similarly, part B, you substitute at what question? What time? Substitute t equal to 1 minute. Substitute t equal to 1 minute, and you'll get equation. The error is same. In this equation, you substitute t as 1. T as 1. What are you going to get? You'll be getting the answer as x minus y will be equal to 0.1986 0.1986 degrees. So this is the difference between the indicated temperature and bath temperature as time progresses after the disturbance. So 0.1 minute after the disturbances, there is a difference between the true value of the bath and the temperature indicated by the thermometer. There's a difference of 0.0786, and it increases to 0.1986 at 1 minute after the disturbance. So these are the answers for part A and B. For the remaining two parts, part C and D, we will continue in the next video lecture. I'll solve for part C and D in the next lecture, and there we'll also be seeing a new term in the next video. So please stand by for the next lecture.